right, here's the good news. Dot product is easy to calculate. Definition of dot product is that if we have two vectors, one that's u, which is u sub 1 comma u sub 2, and v, which has a component form of v sub 1 comma v sub 2, the dot product of u and v means that you take u sub 1 times v sub 1 and you add u sub 2 times v sub 2. So if we take two numbers, multiply them together, take two other numbers, multiply them together, and add them all together, we end up with a single number, a scalar. So our result of a dot product is a scalar, not a vector. And we're going to use the dot product to be able to determine what's the angle between two vectors. So first of all, if vector v is negative 2i plus 5j in our linear combination form, and vector w is 4i plus j in its linear combination form, and we're trying to find v dot w, let's first write them in component form, like we see in our definition of dot product. Negative 2, 5, dotted with 4, 1. What are we going to do? Multiply negative 2 times 4 and 5 times 1. And what do? Add. So negative 2 times 4, negative 8, right? Negative 8 plus 5 is going to get us negative 3. Not too bad, right? Second example, if u is the component form 2, 1, and v is a vector with component form negative 1, 0, find u dot v. Everybody get negative 2? Okay, so it's a scalar, not a vector. Just a plain old number. Okay? All right, questions on this one? All right, next slide. So this is on page 431. You don't have to madly copy it down. Okay, just write in your notes, see page 431 for the properties. Okay? And we'll talk about them. So first of all, if u, v, and w are vectors, and we have a scalar c, then it makes sense that as we take the dot product of u with v, it should be the same as with v and u times dot u, right? Doesn't matter if I take the negative 8 plus 5 or the 5 plus negative 8, right? We're still going to get a negative 3, commutative property of addition. So that one makes sense, right? It also makes sense that if I take 0 times a vector, I better get 0 back, right? Or 0 dotted with a vector, 0, 0 dotted with a vector. And likewise, if I'm taking a vector and I'm dotting it with the sum of a vector, that would be the same thing as the vector, the first vector dotted with the second, plus the first vector dotted with the third. Make sense? It's acting like a distributive property. So it says the distributive property for dot products holds. Okay? Number 4 is kind of surprising, because what does this symbol mean? Magnitude. Okay? So why would a vector dotted with itself give us the magnitude of the vector squared? Let's think about that. If vector v has a horizontal component of A and a vertical component of B, then if I dot it with itself, that means I'm taking A, B, and dotting it with a b. Yep, a squared and b squared, right? And then we're adding them together, right? So it would make sense that if this is a squared plus b squared, the only thing missing for the magnitude is the square root symbol, isn't it? So that's why it's the magnitude squared. Does that make sense to everyone? Okay. And lastly, if I take a scalar and I multiply it by the dot product of two vectors, this is the one that's a little bit counterintuitive, okay? It's either the scalar times the first dotted with the second, or the first times the scalar dotted with the second, okay? You don't want to multiply it twice, right? Which makes sense. We wouldn't necessarily multiply something twice. We only distribute it through when we're adding. Okay, does that make sense? Uh-huh. Absolutely. You can use u dot v and then take that number times c. Okay? Or you can take c times one of them and then dot that with the other, and you're fine, as long as you don't take c times both and try to dot them afterwards. Okay? Any other questions on this slide? Okay, so next, we're going to use the dot product to find an angle between two vectors. So if theta is the angle between vectors u and v, they're non-zero vectors, in other words, they have some sort of magnitude, right? Then the cosine of theta is going to be equal to u dotted with v over the magnitude of u times the magnitude of v. So this is what I'd star in your notes because you'll come back to it. I need to be able to find it. So if we are finding the angle between two vectors, the cosine of that angle is the same thing as the dot product of those two vectors divided by the magnitude of the first times the magnitude of the second. You're welcome to take it in here or back in City Hall. It doesn't matter. Calculator's fine. All right. So far, so good? Now, there are technically an infinite number of angles between those two vectors, but the shortest angle between them is what we end up finding. And if the angle between those vectors is 0 degrees or 180 degrees, that turns out that those vectors are parallel. Okay? So let's find the angle between vectors v and w when v is negative 2i plus 5j and w in linear combination form is 4i plus j. So we defined our vectors, our dot product, in component form. Let's switch it to that real quick. So what's the dot product of the two? Negative 3. Everybody get that? We dot them. We get negative 8 plus 5, which is negative 3. All right, so we know that we need the dot product over the magnitude of the first times the magnitude of the second. So how do we find the magnitude of v? Negative 2 squared plus 5 squared, right? And negative 2 squared is 4. 5 squared is 25. So the square root of 29. Now we need to find the magnitude of w. Okay, so Ray, how do we find the magnitude of w? Here's our w. Okay, We already got that, but we want to find the magnitude now. So magnitude, we want to square root of 4 squared is, and 1 squared is, so square root of 17. Okay, so now we have a square root and a square root. Since the indexes are the same, right? They were the same radical signs. That means that we can multiply them together, right? And remember that the cosine of our angle is equal to this. So we don't have to simplify the radical and get it out of the denominator, because how are we going to solve this to find the angle? Inverse cosine. So we need to take the inverse cosine of both sides, and our theta will be equal to second cosine of -3 divided by the square root of 29 times the square root of 17, or square root of 29 times 17. You can keep them all under the same square root symbol. And did you get 97.7 or 97.8 degrees? Okay. That's the angle between these two. Okay. Now let's verify. Let's kind of see if that actually makes sense. We had a vector v that was at -2, 5. So 2 back, 5 up. Here's that vector v. And w was 4, 1. Does it look reasonable that there might be a 97-degree angle between the two? And so that's one way you can check your work to make sure. Kind of give yourself a visual verification. Yes, that looks like it could be more, just slightly more than 90 degrees. So far, so good? All right, questions on this one? All right, so star this guy. It'll be helpful when you need to find the angle between two vectors. Okay, so here comes our next one. So next we want to talk about orthogonal. Okay, orthogonal is used to describe vectors that are perpendicular to each other. Okay, we want them to make right angles. So remember that if we're looking for the angle, the cosine of that angle is equal to the dot product of them times or over the product of the magnitudes of each. So let's think about that. What would happen if we have a 90-degree angle? What's the cosine of 90 degrees? 0, right? Okay, so if this was a 90-degree angle, the cosine of 90 is 0. So if that's going to happen, what do you know about the right side of this equation? In order to get a 0, we can never divide by 0, right? So the 0 has to be in the numerator, right? So that means that the dot product has to be equal to 0, which forces there to be a 90-degree angle between our two vectors. Okay? So if the angle is 90, the dot product is 0, and that forces the vectors to be orthogonal. So we could have a vector going this way, and another vector going this way, and that theta will be 0 if their dot product. Theta will be 90 if their dot product is 0. Make sense? Okay, not a big stretch there. So, decide whether vectors u and v are orthogonal or not. They are y. They equal 0 because negative 2 times 6 plus 3 times 4 gets us a negative 12 plus 12, which is 0. So yes, they are orthogonal. Easy, right? Okay. Nothing too earth-shattering this chapter. Okay, law of sines, law of cosines was pretty easy. Vectors, there's nothing really to be afraid of, right? We just have to use our heads and remember a few things. Okay? All right, so here's our last example. So we want to talk about work. And you know from physics class that work is equal to force times distance. Okay? The force is the component force in the direction of the motion. And D just stands for distance. So, if we have a tractor pulling a log 800 meters, and the tension in the cable connecting the tractor to the log is about 1,600 kilograms, and the direction of the force is 35 degrees above the horizontal, we want to approximate the work done when pulling the log. So the moment you see work, you write down your work formula. What was work equal to again? Yeah, force times distance. So what is the 800 meters? The distance. And so our force has to come from the 1,600 kilograms at 35 degrees, right? So we've dragged this thing along 800 meters. And we know that we have an angle of incline that is 35 degrees. And the tension on this guy is 1,600. It ran into the blue of his pants, so we'll move it over here. Okay. So we have an angle and we have a magnitude, right? So what was our formula to put something into component form when we knew the angle and we knew the magnitude yesterday? Absolutely. Okay. And the first part gave us our horizontal component, right? And the second part gave us our vertical component. So is the tractor pulling this horizontally or is it pulling it vertically? It's pulling it horizontally, right? Okay. So in order to find our force, we're only concerned with the magnitude times the cosine of theta. Okay. Had we been suspending something, picking it up, right, rising it straight up, then we want our vertical component. But we're pulling this along the ground, so we want our horizontal component. Does that make sense? So when you see the Chevy half-ton pickups being suspended from a cable or something like that, and they're talking about the force on the box and so on, that's because they're lifting it, raising it. We're dealing with the vertical component. But if we're dragging something across the floor, it's the horizontal component. Make sense? So we're going to take our magnitude, 1,600, times our cosine of 35. Should have done it the opposite way. My bracket the other way. So 1,600 times the cosine of 35 times 800. Make sure you close your parentheses after your cosine 35. Did everyone get 1,048,515 or 14.6? Okay. So now our unit's going to be a little weird, right? Because in physics, what do you typically measure units in? Joules. Work is measured in joules, right? We're not going to take the time to convert it to joules. So we're going to call this kilogram meters, right? Because we multiplied the two together. It should be a lowercase k. Questions on this one? Okay. So assignment, going to go nice and quick. Doesn't take really long.